Hey Algebra 2, hope you guys are doing all right, keeping up with Khan Academy work and staying healthy and staying safe and staying happy. Um, so I wanted to do a quick kind of summary video of the stuff that we've learned so far, arithmetic and geometric sequences, just to kind of add to what the videos that you're seeing on Khan Academy, and maybe this will kind of present it in a slightly different way. So I want to see if this will help out. So starting with arithmetic sequences, Khan Academy tends to use this notation for like the first term in a sequence, the second term, so like A of 2, or you could call it whatever letter, G of 2, G of 3, so on and so forth. They're doing that. A lot of times you also see this written with subscripts instead. It'll be A with little subscript 1. That'll be an option as well. A sub 2, A sub 3, A sub 4, and then like when you get later on into like the recursive formulas, instead of it being like C of n minus 1, it'll be C sub n minus 1 with a little subscript instead. So you'll see it both ways. Khan Academy, he even actually switches a little bit every once in a while in his videos. He'll go to the subscript mode, but so I'll try and match this. I might slip into writing subscripts, so I'll try not to. But it can go both ways. It can be done both ways. So the idea of an arithmetic sequence, it's a pattern of numbers, and the whole idea is that we're adding some constant number. So to get from one number to the next number in the sequence, we are adding some constant, we call it d, to represent a difference. All right, so we add d, and we would add d to get from this term to the next term, and we would add d one more time to get there, and so on, and that would continue potentially infinitely, or you might have a finite sequence. I'm not going to mess with that for now. I'm just going to go all infinite for now, but that's the pattern. All right, we're adding a constant amount. So if you have some starting amount, which I'll just call it a, since I think that's what he did. So we are doing this because I'm using that a notation here. I'll say a, if that's a as our starting amount, well, if I add d to that, my second term would be a plus d. And this, I'm doing a generic version first, and then I'll come down to the numbers here. And so then so that's my second term. My third term, if I start with a, I'll have added d to this previous term as well. So if I add d to that term, I'll have a plus d, or a plus 2 d's. And then my fourth term in this sequence would be a plus 3 d's. All right, so that's a few different ways of thinking about this. So if I come down here to some actual numbers, and so I kind of want you to be able to go in and out between these different methods. If I come down here between these different numbers, if I go from 3 to 5, apparently the difference that we're adding there, and if you kind of check this pattern as we go, we're doing plus 2. So this is a pretty simple one, plus 2, and from 7 to 9 it's plus 2, and that pattern presumably is going to continue. So that's 2 is the d right now. 2 is the difference. So our starting term is, another way of thinking about this 3 is that is 3, and then that 5 is 3 plus a 2. All right, so that's my my second term, and I think I'm going to call these ones b. But so that I've added 2, and then this one we've done 3 plus 2 2 times, so it's 2 2's. We wanted to write that way. So 3 plus 2 2's gives us that 7, and then our fourth term in that sequence is 3 plus 3 2's. So the fourth term I've added 3 2's. All right, and so another way you can think about dealing with that one. So if we want to write these patterns out, we can do it 2 different ways, or maybe more, but 2 ways that we're focused on, recursively and explicitly. So recursively is the easier way, I think, to write the formula. There's not a ton of thinking that goes into it, but that's an easier one to write, but not as easy of a one to actually use. Whereas the explicit formula, it's harder to write, a little bit harder to write, but a little easier to actually use that formula. So the recursive formula, what we do is it's kind of a nice way of defining the pattern. What I can say is something like this: a of n, where n is like the number of the step we're on, right? So like n was 1 here, 2, 3, so on. So any particular term in that sequence, the fourth term, the fifth term, whatever, what you do is you look at a of n minus 1, you look at the previous term, And what are we doing? Well, we're adding some number to it. In this case, we're going to be adding a difference, whatever d is. So that's part of the recursive definition. The problem with this, so I'm basically, the recursive part is I'm defining each term in terms of the term that came before it. The problem with that is I do need a starting point. If I don't know what a sub 1 is, to know to get what a of 1 is, I'd have to plug in a of 0. So we do need a starting term when you do it this way. So you have to define a starting term, and then you can go from there. So then I would say a of 1 equals, and then I have to have some number it starts with, and for now I'm going kind of generic, I'm just going to call it a. But to show that down here, for this particular sequence, a of 1 would be 3. All right, so it starts at 3. The first term is 3, and then a sub, and I can define, this defines any term, but the problem is it uses the previous term, so a of n minus 1. So if I want to know the second term, if I plug in 2 for n, then I need to know a sub, or a of, not sub, a of 2 minus 1, so the a of 1. So it's basically a of 1, and then that plus whatever the difference here. In this case, my difference is 2. So my difference up here, I just call d. Down here, it's actually 2. I actually have a number. And so there is a recursive definition of this sequence. And so we can go from there. If I want to know a of 6, though, the 6th term in this sequence, well, that means if I plug in, so I'm plugging in 6 for n, so 6 minus 1, so I need to know the 5th term. Well, that's kind of annoying to know the 5th term, so whatever, it's the 5th term plus 2, that's true. I don't know what the 5th term is. So what is the 5th term? Well, I could figure out the 5th term, but I would have to know the 4th term, and to know the 4th term, I'd have to know the 3rd term. So that's kind of the annoying thing about the recursive definition. You can kind of only go one at a time. If I know A1, I can figure out A2, and then if I know A2, I can figure out A3, and so on, and I can keep adding 2. So it's an easier to define, I think, but harder to actually use, right? So, and I know that the 4th term is 9, and that that came from the process of adding 2, adding another 2, adding another 2. So we know we got there. All right, so then probably the more useful sometimes for finding terms in the sequence kind of further down the line rather than just the first 2 or 3 numbers is the explicit definition. This one does not depend on the previous term. So we can define all of the terms in this sequence following this, in an arithmetic sequence following this particular pattern. So a of n. So if we look back here, we can do it in terms of the difference. So at the beginning I just had a, so we start with a, and then we add the difference some number of times. So I add whatever that difference is that I'm adding, d. So we're adding d some number of times. The number of times that we're adding it, so on the first term I haven't added any d's. So that should be 0 on my first term. But then on my second term I've added 1 d. On my third term I've added 2 d's. On my fourth term I've added 3 d's. So notice fourth term 3. It's always one less than the step that we're on. So the number of d's that we add is n minus 1. And this lets us define, I don't need a sub anything. All I do is we need to know what our difference is, and then we plug in whatever number we want. We can figure that out. So let's see how that works with actual numbers. That sometimes that's nicer to do. So this sequence here, so I start with 3. So I guess I called this a, but I'll stick with it. So a of n is equal to, I start with 3. So you always have your starting term plus the difference. The difference that we're adding here is 2. So I'm adding 2's. How many 2's am I adding? Well, it's going to be that pattern always, n minus 1 2's, right? Because on my first term, I've added no 2's. On my second term, this would be my second term, I've added 1 2. On my third term, I've added 2 2's. So third term goes down to 2 2's. Fourth term is down to 3 2's. So you just do 1 less than whatever term you're on. So now I could figure this out. On my 7th term, I can plug that straight into this formula and figure out what my 7th term will be in this sequence. And so this is much more useful. This is actually shows up on like ACT type questions. They might say, oh, if this is the pattern, what is the 50th term? Oh crap, I don't want to have to go through this 50 times adding 2, but I can use this formula to figure that out. Well, that means I'm going to add 49 2's, and so 49 2's is going to be, what is that, 98? Yeah, 98. 98 plus my initial 3 gets me to 101. So my 50th term in this sequence is going to be 101. And so we can use that. And you know, I always have to go that far, but I do see that on ACT, SAT type questions sometimes, where they ask for some extreme number, right? You can see the pattern, but then they ask for way down the line, and that's where the explicit formula. If I tried to use this formula to figure out my 50th term, yeah, that means I'm just going to basically add 250 times, which is what this is effectively doing. It's just doing it kind of more efficiently. All right, so then what if we start in a different format? What if I start with the recursive formula? Can I get to the other two from that? Yeah, it's not too bad. We have our starting term, so if this is my first term, so my first number in my sequence here is a 15. And then from there, our pattern is for each term, in this case, I take the previous term, so I'm calling this C. C of n is equal to C of n minus 1, the previous term, minus 5. So if I want to know the second term, I can plug in 2 for n. C of 2, which would be kind of my second term here, is equal to C of 2 minus 1, so C of 1 minus 5. So I need to go look at C of 1, which was 15, minus 5, and that will be 10. So that's what C of 2 will be. And then C of 3 would be C of 2, so if you plug in 3 here, the 3 minus 1 is 2, so C of 2 minus 5. So I look at that term, minus 5, and so you can see what pattern is going to arise here and continue on, at least infinitely for this case. All right, so that is going from that recursive formula to an actual sequence. We can also get to an explicit formula as well. C, my eraser, C of n is equal to, well, we always have our starting term, so it was 15, and then here's my difference, right? So that we're subtracting 5 every time. So I'm minusing 5s. How many 5s am I minusing? Well, it's always n minus 1 if we follow this pattern. And so it's 15 minus 5 times n minus 1. So you know, I've subtracted 1 5 on my second term. I've subtracted 2 5s by the time I get to my third term. I've subtracted 3 5s at my fourth term, and so on. At this point, let me maybe make a quick note that you actually, this is the way that it's nice to write it, but you could technically simplify this. I think this is nice as is, but you could simplify that formula and distribute 5. Right, so like this works for no matter what term we plug in, right? I could plug in 0. Sorry, not 0. The first term, I could plug in 1, and 1 minus 1 is 0, and then I multiply that times 5, and so I end up with 15 to start with. You could plug in whatever you want. You could distribute that negative 5, so this is kind of an optional thing. I guess let me change up for this. So if I could optionally distribute that negative 5 and end up with 15 minus 5n plus 5, and then combine those, and I get 20 minus 5n. It's mathematically the same. So it's 20 minus 5n. So now if I plug in 1, it doesn't like cancel to 0 like it did before. It's just 20 minus 5 gives me 15, and that is my first term. And then we can plug in 2, and so it works the same. It's not it doesn't work as nice logically, and we could do the same thing here. It'd be like, you know, you could distribute the d, and so this ends up being dn and then negative d, and so you have a minus d plus dn. It makes less sense ultimately, I think. So this is the nice way of writing the formula in terms of understanding, but you could actually have another linear, this is a linear equation, by the way, this explicit formula, because linear growth is a constant growth where we're growing by the same difference, the same amount. All of these are actually linear patterns. We'll see that change when we get to geometric. But it could be written another way. I just wanted you to see that is a possibility. All right, last one for this case is what if we're given an explicit formula? Can we figure out the other ways from that? So yeah, if we just basically can plug in, what's my first term? Plug in 1. All right, well, 1 minus 1 is 0. 0 times 4 is 0. And so I end up with negative 6 plus 0, and so I just get negative 6. That'll end up being your first term. So my first term in my sequence is negative 6. My next term, plug in 2. My second term, plug in 2. And so 2 minus 1 is 1. 1 times 4 is 4. Negative 6 plus 4 is negative 2. And so negative 2. And what we can see is going on here is that we are adding 4 every time. And my third time, when I plug in 3, I'm adding 2 4s. And so we can kind of see that pattern start to arise, and it kind of becomes easy, and you can just jump over here and start adding 4 to each number, and until you are sick of it, and you can write the dot dot dot. But yeah, I could have plugged in my 5th term here, 5, and I would say, oh yeah, I'm adding 4 4s, so 16 to negative 6, and you get that positive 10. And if I want to know my 20th term, I could go figure out my 20th term before I figure out my 19th term. That's the nice thing about that explicit formula. You can just plug and straight in. If we are going to write this recursively, I mean, we could go back to this. We can also think about, all right, so we're starting at negative 6, so d of 1 is negative 6, and then each time, what are we doing? And this is kind of always the same format, so I have d of n is equal to d of n minus 1. That's kind of the recursive idea. That's the whole thing, is look at the previous term. Sometimes you can get into fancier things where you're actually doing multiple previous terms with different types of patterns, but for now we're just sticking with this one. So the previous term, and then ultimately we're adding 4s. Right, that's the difference that we're adding here, plus 4, and that would be defining that recursively. So there we go. There's arithmetic sequences, both just defined as the sequence, recursively and explicitly, and kind of going back and forth between those. I'm gonna stop this video. I'll do another one. Got the geometric stuff on the back. So I'm gonna do another one in a second if you want to take a look at that one as well.